In the first video, I spoke about two steps for dealing with constraint optimization problems. Here our problem is where we maximize f of x comma y subject to the constraint g of x comma y equal to the constraint constant c. So the two steps that I talked about in the previous video were as follows. First of all, set up the Lagrangian function, which is L, and note here that this Lagrangian function is also a function of some variables, and that is why you get these choice variables. So L is a function of x, y, and lambda. So anyway, so your Lagrangian L is nothing but your function f of x comma y plus the Lagrangian multiplier lambda times the constraint constant minus the function g of x comma y. So this is the format that we're going to follow. So please remember this format. We're going to start with the main function f of x comma y. Add to that the Lagrangian multiplier times the constraint constant minus g of x comma y. Your book, there are some books which also write things this way, where they put minus in front of lambda, but then the stuff in brackets would become g of x comma y minus c. It amounts to the same thing. So those two things are equivalent. Anyway, so that was the first step, and as a second step we said we have to find the optimal x, y, and lambda, the stationary point right now actually. So we set up the first order necessary conditions and put all those equal to 0. So that is the second step of dealing with a constraint optimization problem. But as you already know that these first order conditions are necessary conditions. So to check for the sufficiency, to check for whether you actually have a max or a min, you have to look at the second order conditions, and there for that we set up what is known as, so this is step 3, we set up what is known as the bordered Hessian. Right, now what exactly is a bordered Hessian? This is a matrix that we set up, so, and we check for the determinant of that matrix. Now the bordered Hessian is given by this determinant 0 g sub x. So basically the partial of the partial derivative of the function g with respect to x, g sub y. And now here you see why we call it a bordered Hessian, because this is bordered by, you have this 0 g sub x, g sub y acting like a border, and in the center you'll have the regular Hessian kind of determinant, the terms L sub xx, L sub yy, L sub xy, L sub xy, L sub yy. So this is your bordered Hessian, and if the second order condition, sufficient condition, is that if the determinant of the bordered Hessian matrix is greater than 0, now you're going to have a max at the stationary point. So this is a little contrary to what we've been doing earlier, where when we used to get a negative definite Hessian, we used to call that a max, conclude a max there. But now just check for the sign. So when the bordered Hessian determinant is positive, then you conclude that you have a max at the stationary point. And similarly, if the determinant is negative, that implies that you have a min at the stationary point. Okay, so these are the 3 steps that you have to look at. Now let's take up a specific problem, our utility maximization problem, and see how that will pan out in this framework. Okay, so our problem is maximize u of x comma y. You have two goods, x and y, and you're maximizing utility subject to the budget constraint, price of x times x plus price of y times y is equal to money income. So here your Lagrangian will become u of x comma y, that is basically this u function is your f of x comma y function, and this p x times x plus p y times y is nothing but your g function, right? So you'll write the Lagrangian as u of x comma y plus the Lagrangian multiplier times the constraint constant, which is m, minus this g of x comma y function. So that's price of x times x minus price of y times y. This is your Lagrangian. And now when you look at the first order necessary conditions and put them equal to 0, you're going to get the following first order conditions. Your partial of the Lagrangian with respect to x is going to give you u sub x minus lambda times the price of x, right? Because you're going to take the derivative, the partial of u with respect to x, plus lambda times minus the price of x, because you're taking the derivative with respect to x. Put that equal to 0. Then L sub y, which is a partial of L with respect to y, that is going to be equal to u sub y minus lambda times the price of y. Put that equal to 0. Then the partial of the Lagrangian with respect to the Lagrangian multiplier lambda is equal to nothing but the constraint itself. So that's your money income minus price of good x times x minus price of good y times y. Put that equal to 0. So this is going to give us 3 equations, and let's see what information we can gather from these 3 equations. So first of all, if you notice, if I just take equations 1 and 2, this is an exercise similar to what we did in the previous video. The first 2 equations imply that u sub x is equal to lambda times the price of x. This is what we get from the first equation. And from the second equation, we get u sub y is equal to lambda times p, the price of good y. And taking the ratio of these 2 equations, the left hand side and the right hand side, the way we did in the previous video, we'll see that once we take the ratio, the lambda terms here get cancelled, and what you get is u sub x, the feature of the equilibrium condition that I had talked about. So u sub x divided by u sub y, and we can put in the arguments here just to make things complete, is equal to the price of x divided by the price of y. And this is actually something which you should be very familiar with, because your left hand side is nothing but the ratio of the marginal utilities. This is the marginal utility of x divided by the marginal utility of y, which is nothing but your marginal rate of substitution, the slope of the indifference curve. And we are saying that in equilibrium, the slope of the indifference curve must be equal to the price ratio, right? So this is reflecting nothing but the tangency condition in equilibrium, where your budget line is going to be tangent to the highest possible indifference curve. So the equilibrium will occur at the tangency point. Okay, so this is where your equilibrium condition starts coming into the picture with respect to economics problems. Now, what you could do as an exercise, let's put in some numbers here so that things become more concrete. Or let me take it up in the next video, because this one is getting a little long.